this is where you're going to see live demonstration of people actually using Genie to do the research. So this time the demo is going to be out of a Clemson team. So Geddings Barrineau is a graduate student working with Professor Wang at Clemson University, and he's going to talk about the work they're doing with using the SDN network to enable other researchers. So they're actually working with bioinformatics and people from medical, like some surgeons, and they're going to talk about the research. And I want you to focus on like how they're using the different tools that they have, like from Genie to Cloud Lab to AL2S, and how they're like actually building a production service that other researchers can use. So, Geddings.
Okay. Everyone hear me okay? That's good. Thank you for the introduction. This is my first time up here, so I'm pretty nervous. So I just ask that you do one thing for me and make sure you laugh at all of my jokes. Worked super hard on this. So if you've been hanging around Genie long enough, you might remember from about a dozen GECs ago, we first introduced our first iteration of SOS. And SOS really has its roots in transparent proxies. And so this started as kind of a fun use case of OpenFlow, back when OpenFlow was getting pretty popular. And logically, it kind of transitioned into us asking the question, how can we help the research community at large? And so we're going to keep going. Shortly after that, there's our logo, by the way. You like that? Shortly after, we ran into a group of geneticists who were fed up with how they were transferring data. They had these huge links, these long-distance links, trying to transfer large DNA data. And it was just going slow. They were getting terrible throughput. And so part of that was they were using these very simple data transfer tools. And they were using wget, using curl, FTP. And as most of you probably know, under the hood, these are just simple single TCP connections. So TCP, let's see where we're at. Current TCP congestion and flow control algorithms really struggle at filling high delay bandwidth product links. They just can't do it. And so another thing that these geneticists try to do, I mean, they're tired of it. They're tired of having these huge links, getting these slow speeds, huge data sets taking weeks to transfer. So they transitioned into more complicated applications. These are software-based. They would have to install them on their machines. They would have to install them on their server machines. But the big issue for us that we saw was it really required them to have an understanding of networking that they really shouldn't have to care about. So in our opinion, this is very much a networking problem, and so it should be fixed in the network. So you are a researcher, you're a geneticist, you have this laundry list of problems, so who are you going to call? It's not the Ghostbusters, it's the Clemson OpenFlow group, and we're going to give you SOS. Yeah, you can laugh, it's okay. I appreciate it. So what is SOS? SOS, our solution, is we're going to use the known benefits of parallel TCP. So this TCP windowing problem is not a new problem. It's already been solved, and so this is not really what SOS is about, but we're going to leverage the benefits of parallel TCP, but we're going to abstract it away into the network, and we create a network service. And we do this using SDN techniques, and I'll show a little bit more about that in a second. And we've done it in a way that's scalable, and so as more people want to use SOS, we can add in more resources to cope with that. So a little bit about the architecture. It starts with the agents. So I mentioned earlier about transparent proxies. So that's essentially what these agents are. They're transparent proxies. And really, it's simple. They're persistent C programs. They're just running and running and running and waiting on TCP connections. These agents handle all of the parallel TCP. So they abstract it away into the network so the client, the person trying to transfer this DNA data, doesn't have to care about it. The agents handle all of that. And so these agents, let me see if I can show you. These, obviously, you can read. These are agents right here. Next, we have OpenFlow switches. These switches are responsible for matching on packets. They're responsible for rewrites and redirecting packets to the agent. And we use these OpenFlow switches to create this transparency. We have the controller, which, like the name implies, it controls the network. It's responsible for all the setup and the teardown of SOS connections. And it's also responsible for communicating with the agents to let them know the type of parameters we're going to use for a specific SOS connection. And finally, I just want to mention really quick about the clients and the servers, which are, sorry, first time with laser pointer. These are clients and servers. These are completely unmodified. And so I mentioned solutions today that use parallel TCP. They're applications that are installed on a computer, on the computer of the person that's trying to use it. But with SOS, the clients and the servers are completely unmodified. There's no configuration needed. There's no applications to be downloaded because they are completely unaware of SOS's presence in the network. So they get all the benefits of parallel TCP and increased throughput without having any of the overhead that these researchers don't care about. So I have a demonstration. Well, this isn't a demonstration, this is more of a diagram. I need to preface this with there are three major components with SOS. I'm going to try to use a laser pointer here. There's the server to agent. That's the first major component. There's agent to agent. That's component number 2. There's agent to client. That's the third major component. And so we're going to assume here, for our purposes, that the client wants to download something from the server. It wants to download a DNA data file. And assume that the TCP handshake has already been done. So you want to download a cat DNA data file. You want to find out why this cat has 3 tails on it. And so the server is going to go and it's going to attempt to send to the client. And so your DNA data is going to get to the physical OpenFlow switch. Some rewrites are going to occur, and it's going to be redirected to the agent. I want to reiterate, the server does not know this has happened. The server thinks he is sending to the client, but in reality, the agent has received some data. So the agent's going to reply with an acknowledgement, going to get rewritten, and so the server thinks it just got an acknowledgement from the client. So from the server's perspective, it sent some data to the client. So that's the first component. So the second component, we're going to assume that the server has been sending data to its local agent, lots and lots of data. The agent has built up a buffer, and it's ready to send over lots and lots of parallel TCP connections to the other agent. So we've actually gone as high as 7,000 parallel connections. We have all of our data. We're going to send it across. These are just regular TCP connections. And then the other agent's going to reply with its acknowledgements. And that's it to the second main component. And finally, this is the third one. And the third major component is really just the same as the first. It's just in reverse. So I'm not going to talk too much about that. Get you guys out of here quicker. So sending data to the client thinks it's received data from the server. The client's going to reply to the server, and that's going to get rewritten and go to the agent. I've got a video of all this happening. It's important to realize that all of this is not disjoint. This is all happening. So as this is sending data and this is built up buffers, this is sending data also. When this has enough data, this is sending. So assume this next video has been steady state. This is just everything all together. And it looks super complicated, and that's okay. This is why we have a demo night, so you can come ask me lots of questions about this in particular. The next slide. So some of our results, we have a link between Clemson and Utah that goes over AL2S. It's a 10 gig link. And some of the results that we've gotten, these are memory-to-memory results. Without SOS, we've achieved 180 megabits per second, so about 2% utilization of the link, which is awful. So as a researcher, you can see why this is a huge problem, because you're trying to transfer hundreds of gigabytes of data, sometimes even thousands. This might take weeks. With SOS, however, we were able to see about a 30 times improvement and get 5.3 gigabits per second, so about 53% utilization, which is good, but our goal is 100% utilization. And so we did some detective work, and we discovered that the Utah agent was actually using 107% of its CPU, which is a problem because every component in SOS needs to be giving 110%. That was also a joke. 107% utilization is bad, and so thank you for laughing. 107% utilization is bad, and so we brainstormed, what can we do? Well, we could buy a bigger agent, one with a better CPU, but eventually, as links get too big, even the best CPU in the world is not going to be able to keep up. And so this guy's thinking about scalability. Can we add in more agents as we need them? And so Genie is a perfect testing environment for this. And so we made a slice, from Cornell to Stanford, and we have 3 agents on each side. And we ran some tests with and without SOS. We ran it with 1 agent, we ran it with 2 agents, and we ran it with 3 agents. And we discovered that SOS, you can get linear throughput, a linear increase in throughput as you increase agents. This was great news. So SOS, at least in Genie, we discovered is scalable. It was great. So now we have a demo. This is our Clemson to Utah link over AL2S. This is a really complicated diagram. And so what I pretty much want you to see, these are our, see if I can step back. These are our clients and agents on Clemson side. I think, ooh, cut out. Is that you, Ryan? Wow, thanks. This is our server and agent on the Utah side, and we have a 10 gig NIC on each side, so we're limited by that. So my assistant, Ryan, is gonna, we're hopefully gonna give you a live demo of SOS right now. So the top graph is our average throughput, and we also have one on the bottom, which is, if you can read it, a rolling average. This is without SOS right now. But keep in mind, there's a 10 gig link, and it keeps cutting out, and that's okay. So kind of there it is. That's not 0. This is probably between 100 and 200 megabits per second. So right around that 2% utilization that we saw. Not great at all. So hopefully we can see a lot of improvement with SOS. So run again. So this is with SOS, and I think 256 parallel sockets. With that many sockets, sometimes it can take a little while for it to ramp up, which you can see there in the beginning. Normally it settles. So I think we are approaching 5 gigabits per second. So around that 30 times increase in throughput. This is live. I'm very happy with that, and that's really good. Makes me happy. Okay, so I'm gonna turn that off. Oh yeah. So future work. This is great, and we're really excited about this. But currently, we are trying to test scalability in Cloud Lab. We tested in Genie, and you saw the results. But Cloud Lab provides us with the resources that are going to be similar to the resources that these geneticists are going to have at their disposal, or these bioengineers or bioinformaticists. And then along with that, we are also working directly with bioengineers to deploy SOS as a network service for use by laparoscopic surgeons. And so this scary looking robot right here performs laparoscopic surgeries. And what we're trying to do is, we are, what would the word be? I think of it. Yeah, we have these cameras pretty much, and they have extremely high bit rate, so about 1.5 gigabits per second per camera, and normally there's 2 or 3. And we're trying to display real-time footage on top of someone that's being operated on. And the reason we're not using UDP is because we are also analyzing this data. In UDP, sometimes you can have traffic get cut out, and so if you're under the knife, you really don't want that. You want reliable. So SOS, this is a perfect use case for us. But yeah, I think that's about it. If you have any questions about anything, we'll be at the demo night. We'd love to talk to you. Please come by. And thank you for having us. We're very, very thankful.